In this lecture, we will study a very small but very important topic, which is the theorem of constant flux linkages. This theorem is utilized at many places, especially when we do the modeling of synchronous machines during fault. This theorem is invoked at many places to derive the equivalent circuit model of those machines. So let us see what is the meaning of this theorem of constant flux linkages. For that, on the board I have drawn some circuits. So let us see what do I want to show here. For the circuit A, let us say this is the flux phi linking with the coil. So if I want to write the loop equation or the KVL equation inside in this circuit, what I will write, Ri plus d by dt of Li is equal to 0. Okay, now if I assume that R is equal to 0, that is the resistance of the circuit is equal to 0, this is for the circuit A. Okay, so it implies that d by dt of Li is equal to 0. Now what is Li? Li is nothing but the flux linkages of the circuit. This closed circuit is having flux linkages given by psi is equal to Li. As we already know that inductance of the circuit is nothing but the flux linkages per unit current. Okay, so you see that from this equation what I can get, that the flux linkage of the circuit is a constant. So what is the meaning of theorem of constant flux linkage? It says that for a closed circuit, so there are two conditions, that is the circuit should be closed one. Okay, so this is a closed circuit here. If resistance is equal to 0 or negligible, then its flux linkages is equal to constant, that is they cannot change. Okay, now here I have used the term flux linkages instead of flux. Why is it so? Because I want to show that even if flux links with half number of turns, then we will have to use only those flux linkages which are linked with that circuit. Okay, according to the number of turns which are linked. Instead of writing just flux, I want to clearly show that it is the linkages of the circuit, not just the flux. Okay, so from this definition or this circuit, I have clearly shown the concept of theorem of constant flux linkages. Now what I will do, I will try to further elaborate the scope of this theorem. So for that I have drawn another circuit B here, in which what I have shown that this is the circuit and let us say it is a closed one. Okay, now this circuit is having an iron core, the self inductance L, and it is mutually linked with another secondary circuits, circuit 1 and circuit 2. Okay, and the mutual inductance coefficient is M1 and M2. Now I will write the equation for this circuit after erasing this. Now for this circuit, if I want to write the circuit equations, the loop equations, it comes out to be Ri plus d by dt of Li plus M1 I1, this is the I1 and this is the mutual coupling coefficient, and similarly it is having flux linkage because of this also, M2 I2 is equal to 0. So again this is a closed circuit. Okay, and if R is equal to 0 according to the conditions of our theorem, then we can clearly see that d by dt of Li plus M1 I1 plus M2 I2 is equal to 0. So what is this term? This is these self linkages, flux linkages, and these comprise the total mutual flux linkages. Okay, so these should remain constant for the given conditions. Okay, that is, if R is equal to 0 and the circuit is a closed one, these cannot change. Okay, these should remain constant. So again, I have increased the domain of the scope of the theorem of constant flux linkages. Now we will further increase this domain after studying this circuit C. That we will see after erasing this. Now in this circuit C, what I have done, I have shown a circuit A which is a closed circuit comprising of self-inductance LA, LB, LC and LD. Okay, resistance RA, RB, RC and RD, although we will neglect those, and the current is IA, IB, IC and ID. Now this circuit, closed circuit A, is having another secondary circuits. This is LG, RG and current is IG, similarly LF, RF, IF, and these are other secondary circuits which may or may not be moving with respect to this circuit, that is, they can be in motion. So here what I want to do is that I want to further elaborate the scope of this theorem to motional EMF also, okay, or motional flux linkages. So let us say there is some motion also, and because of that there is some mutual coupling. Okay, now I will write the equation or the loop equation for this closed circuit here. IA RA plus IB RB plus IC RC plus ID RD. This is the drop in the resistances, plus d by dt of LAIA, LBIB, LCIC plus LDID. So these are the self one. Now let us say it is having mutual coefficient Mg for this one, Ig plus M E IE plus MF IF for these inductances. Okay, similarly let us say this is having mutual coefficient or the motional coefficient for these circuits, M1 I1, M2 I2. So if there are so many other circuits, we can further generalize it, equals to 0. Now if I further assume that R is equal to 0, then this term is equal to 0. So what does it say? It says that the total flux linkages are constant for this closed circuit. Now I will try to further show one more thing. Let us say we are again writing equation for this circuit. So Ri plus d by dt of Li is equal to 0. Okay, so minus d by dt of Li is equal to Ri. So what does it mean? It means that if we do not approximate the resistances to be equal to 0, then the theorem of constant flux linkages will say that the flux linkages of the circuit, the closed circuit, will change with a rate such that they induce a voltage which is just equal to the voltage drop in the resistance part of the circuit. So we can modify the theorem to include the effect of resistances also. Now in the next slide, what I will do, I will try to formulate 2-3 questions based on this, and we will try to solve them so that we can finally get the grasp of the concept involved in the theorem of constant flux linkages. Now here in this slide, I have drawn 4 pictures to show 4 different scenarios, and we will try to apply the concept of constant flux linkage theorem, and we will see what is the outcome of that application. Here what I have done, I have tried to show 4 scenarios. First one is that there is a DC source applied and there are 2 coils, and these coils are not having any resistance. That is, R is equal to 0 for these coils. Okay. So initially this switch S2 is open and S1 is closed. So what will happen? A current I1 will flow, and I1 will just depend upon V over R1 by Ohm's law, since it is a DC circuit. Now the I1 will create a flux phi 1, which will be comprising of 2 parts: the leakage flux phi L1 plus the mutual flux. So the flux will be like this. The flux linking both coils will be phi m, and this flux will be phi L1. Okay. So in this way we have got some flux distribution. Now since this is a closed circuit, okay, so the flux linkages of this circuit cannot change. Or in other words, the rate of change of these flux linkages can be just equal to the voltage drop in this small resistance. Okay, this is made of superconducting material. This is also made of superconducting material. Okay, that is R is equal to 0 for both the coils. Now let us say that switch S2 is closed. Okay, so at this point the flux linkages of the coil 2 is nothing but the flux phi m into the number of turns, and it is equal to just the mutual inductance into the current in the coil 1. Okay, now when switch S2 is closed, then there cannot be any change in I1. Why? Because I1 is governed by V over R1. If it is just V DC, so I1 cannot change. Okay, so the flux linkages will just again be MI1, or in this case also the flux linkages will just be phi m N2 is equal to M I1. Okay, so here again you will find that their current is 0. Here current is already 0 because it is open circuit. Here it is 0 because there cannot be any change now, because it is just governed by this equation. So there cannot be no electrical change in this circuit. Okay, now let us see the third scenario. Now what we are going to do, we are going to open the switch S1. Now you see, this circuit is a closed circuit with 0 resistance. Okay, so according to the theorem of constant flux linkages, the flux linkages will remain constant. It will be equal to MI1, and let us say now some current starts to flow. Okay, so the should be equal to the total flux linkages. Okay, so it implies now the I2 will be equal to M over L2 into I1. Here I2 will be equal to 0. Here it is I2 is equal to M over L2 over I1, where I1 is the value of this current or this current. This is the same in both case. Okay, so I1 will be this value. Now I have further elaborated the scenario. What I have done now, that with a very thin saw I have cut the iron and taken out the coil. Okay, and the coil is taken away from any iron, such that the M is equal to 0 in that scenario. Now we are asked what will be the value of I2 prime. Okay, now this is already open. You see, as this is already a closed circuit, and earlier the flux linkages were L2 I2. Okay, now since it is in air, L2 will change to L2 prime, and it is given, let us say that L2 dash is 0.05 times of L2. Because it is in air, so its value will reduce, okay, because of increased reluctance, but it should always be equal to the initial flux linkages, because it should always remain constant according to our theorem. So L2 dash I2 dash, or I2 dash is equal to I2 into L2 over L2 dash, or it is, for our case, 200 times of I2 by putting this value. Okay, so you see that to keep the constant flux linkages, the current should increase according to the ratio given between these inductances. Okay, now there can be one more question. What can be that? Is that we may be asked to find the work done to bring this coil from here to this place, such that M is equal to 0 and inductance is L2 prime. So what will be that? The work done will be just equal to the change in the stored energy. Now finally the stored energy in this circuit will be here only, half L2 prime I2 prime squared. Okay, and initially it was half L2 I2 squared in this circuit only. Okay, so delta E is final minus initial, so it comes out to be half L2 dash I2 dash squared minus L2 I2 square. Now using these values, now you know that L2 over L2 dash will be greater than 1 for our case, and for similar scenario also this will be true. Okay, so let us put the values here first. L2 dash into I2 into L2 over L2 dash squared minus L2 I2 squared is equal to half L2 dash into I2 square into L2 square over L2 dash squared minus L2 I2 squared. Half I2 squared is common, and this will get cancelled out. It will be L2 common outside, L2 over L2 dash minus 1. So this thing can be neglected as compared to this thing. So it will be just half I2 square into L2 into the fraction, and this fraction is equal to 200. So you see that the work done in moving away this coil will be equal to this value, and it will be depending upon this factor. Okay, this is the initial stored energy and this is the factor which I am talking about. So in this way the work done is very high now. Okay, now in the next slide, what I will do, I will try to show one more scenario so that the total concept is more clear to everyone. That I will do in the next slide. Now let us see one more scenario. Now what I have done, that I have included one more switch, and let us say I close this switch first, that is this S3 is closed first, and this now is a closed circuit with zero resistance. Okay, now what I will do, I will bring this coil again on the iron, that is I have brought this here. Now what I need to find, I need to find the value of I1 double prime and I2 double prime, and this is M. Okay, the number of turns remain same, the inductance will revert to L1 and L2. Now we will be surprised to know that what will happen, that since in this case the flux linkage is, before we brought this here, we closed this switch, so the flux linkages of this circuit were equal to 0. Before we brought this, we closed this, so there was no current I1 earlier, so this thing was 0. Okay, now since it is a closed circuit, the flux linkage should remain constant. Now after we have taken this coil here, now the flux linkages of this circuit will be L1 I1 double prime, this current into L1, plus M I2 double prime, and this should not change, that is it should be equal to 0. Okay, and psi 2 will also not change, which was equal to L2 prime I2 prime. Okay, now it should remain equal to L2 into I2 double prime plus M I1 double prime. Okay, now L2 prime I2 prime is nothing but L2 over L2 into I2 from this equation. Okay, these are the two equations. Now you will find that since there cannot be any flux linkages with this coil, so what will happen, all the flux created by this coil will become leakage flux. There cannot be any mutual flux, there cannot be any phi m. So phi L2 will be equal to phi 2. Okay, so in this way the current induced in the primary will be such that it will drive away all the mutual flux, and all the flux will be just leakage flux for the secondary winding. Now in the next slide we will try to find the expression for I1 double prime and I2 double prime. Now in this slide I have calculated the value of I1 double prime and I2 double prime. From these two equations I can get that I1 double prime is equal to minus of I2 M L2 over L1 L2 minus M square. Now I will write K is equal to M square L1 L2, that is the coefficient of mutual coupling. Okay, it is usually less than 1. Okay, for perfect coupling it will be equal to 1. Now similarly I can find the value of I2 double prime, and it comes out to be I2 into 1 over 1 minus K squared. Now the ratio of I2 double prime over I2 is nothing but the short circuit current over excitation current. Now if we see just previous slide, we will find that I2 double prime is nothing but the current which is flowing when there is a short circuit in the primary side also. You can verify that. Now excitation current, this I2 is just the current which is flowing due to excitation. Okay, so in this way this ratio short circuit current over excitation current is just equal to 1 over 1 minus K square, and this K is depending upon the coefficient of mutual coupling. Okay, now in this way I have tried to solve various scenarios so that the concept of theorem of constant flux linkages can be clear to everyone. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.